So today I want to talk about embeddings of the Heisenberg group and the Sparsest Cut problem. So let me start by saying a couple words about the title. So remember, the Heisenberg group is an object from group theory. It's a nilpotent Lie group. It's the simplest non-abelian nilpotent group. And it can be equipped with what's called a sub-Riemannian metric. So it's really some geometric object. The Sparsest Cut problem is a problem from computer science. It's a question about where the input is a graph, and the question is to find a way to cut that graph into two pieces in the most efficient way possible. So what's the relationship between the Heisenberg group and the Sparsest Cut problem? Well, the Sparsest Cut problem is an NP-hard problem. It's a problem that we have no good algorithms for solving exactly. But we do have algorithms. There are algorithms that run in polynomial time that provide approximate solutions. And one of the best is called the Goemans-Linial relaxation. And the accuracy of the Goemans-Linial relaxation turns out to depend on how well certain metric spaces embed in the Banach space L1. So in particular, the Heisenberg group is one of these metric spaces. And in particular, so you can bound the accuracy of the Goemans-Linial relaxation for the Sparsest Cut problem in terms of embeddings of the Heisenberg group. And so that's what I want to talk about today. I want to introduce the Sparsest Cut problem. I want to introduce the geometry of the Heisenberg group. I want to connect them. And then I want to talk about some previous work on embeddings of the Heisenberg group. And then I want to talk about some work I've done recently with Assaf Naor to get sharp bounds on the non-embeddability of the Heisenberg group in L1. Okay? Okay. So let me start by introducing the Sparsest Cut problem. So the Sparsest Cut problem is a problem from computer science. It asks what's the best way to cut a graph into two pieces. So the input to the algorithm, or the input to the problem, is a graph. And the question is to find the value of this function phi, which is the minimum sparsity of a cut of the graph. So a cut of the graph is a subset of the vertices of the graph, and we think of this as cutting the graph into two pieces, the set and its complement. And the sparsity of that cut is given by this quotient here. The sparsity of the cut is the number of edges from one side of the cut to the other, divided by the product of the number of vertices in one side and the number of vertices on the other. We think of this as the number of actual edges in the graph between the two sides, divided by the number of possible edges in the graph between the two sides. Because if you have an edge from every vertex on one side to every vertex on the other side, you have norm s times norm s complement edges. And so this is the fraction. This is always between 0 and 1. This is the fraction of edges between the two sides. So for instance, here we have a graph with 7 vertices. We've got a clique of 4 vertices and a clique of 3 vertices. What's the best way to cut this in half? What's the sparsest way to cut this in half? Well, we can take all the vertices in one clique and put them in S, and all the vertices in the other clique and put them in S complement. And then we've got 2 edges going across out of a possible 12 edges going across. And so we have a cut with sparsity 1/6. Okay? Okay, so so I've stated this as a graph problem, but you can also state it as a matrix problem. So here's my graph again. Here's the adjacency matrix of that graph. It's a 0, 1 matrix where you have a 1 in a given position if there's an edge between the vertex corresponding to that row and the vertex corresponding to that column. And then we can define phi in terms of this matrix by writing the sparsity of a cut, and now a cut is going to be some subset of the rows and columns. The sparsity of a cut as, well, a cut like this is going to break the matrix into a 2x2 block matrix with some on-diagonal blocks and some off-diagonal blocks. And the sparsity of that cut is going to be the proportion of ones in the off-diagonal blocks, the number of ones in the off-diagonal blocks divided by the size of the off-diagonal blocks. The sum over I and S, J and S complement of the entries of the matrix divided by the sum over I and S, J and S complement of 1, right? So this is the same thing as the first problem. It's just stated slightly differently. What's the advantage of stating it this way? Well, if we write this as a matrix problem instead of a graph problem, then it becomes clear that there's no particular reason why we should be using a 0, 1 matrix here. And there's no particular reason why we should only be adding 1s in the denominator. So we can replace the numerator and the denominator. We can replace the graph with two matrices, C and D, the capacity matrix and the demand matrix, to get something called the non-uniform sparsest cut problem. So now, this is a problem where the input is two matrices, C and D, the capacity and the demand, and you want to minimize, again, the sparsity of a cut, where now our cuts are subsets of the rows and columns, and the sparsity of a cut is divided by, is given by the ratio of the total capacity across your cut divided by the total demand across your cut. Basically, you can think of these matrices, Cij is roughly how difficult it is to separate vertices I and j, and Dij is roughly how much you want to separate vertices I and j. So you want to maximize the demands and minimize the capacities. Is this okay? Okay, so this turns out to be a very general framework for dividing objects in half. And this is very useful in computer science because there are a lot of algorithms in computer science that are based on a divide and conquer technique. You have some big problem, and so you want to cut that problem into two halves, and then cut those halves into smaller halves, and cut your problem into smaller and smaller pieces until they're small enough that you can solve the pieces easily, and then join the pieces back together to get solutions to bigger and bigger pieces of the problem until you have a solution to the whole problem. So if we had good algorithms to solve the non-uniform sparsest cut problem, then that would improve a lot of other algorithms in computer science. The difficulty, though, like I said at the beginning, is that the sparsest cut problem is NP hard. We don't have any polynomial time algorithms to solve this exactly. But what we do have is we have some polynomial time algorithms to approximate the sparsest cut problem, and then these algorithms are based on certain metric embeddings. Okay? So how does this work? These algorithms, these approximation algorithms calculate what are called relaxations of the sparsest cut problem. So what do I mean by that? So if S is a subset of the numbers between 1 and n, I'm going to define the cut metric d sub s. D sub s of ij is equal to 1 if I and j are on opposite sides of the cut, and 0 if I and j are on the same side of the cut. Then I can state the minimization problem that we solved for the sparsest cut problem in terms of these cut metrics. So let's let C be the set of cut metrics, and then I can write the sparsity of a cut as the sum over I and j of Cij times Mij, where m is a cut metric, over the sum over I and j of Dij times Mij, where m is a cut metric, and get exactly the same minimization problem as we saw before. Or what I can do is, instead of minimizing over the cut metrics, I can consider some subset of the matrices of the n by n matrix, some set of n by n matrices K that contains the cut matrices, and then define a different minimization problem, phi sub k, where we minimize this same quotient, except over this different set of matrices. This is called a relaxation of the sparsest cut problem, where we're solving the same problem, except we're minimizing, instead of over cuts, we're minimizing over some set of matrices. And so in particular, what can we say about this? Well, if k is equal to c, if we minimize over the cut metrics, then we end up with exactly the same thing as the original sparsest cut problem. In general, if k contains c, then the minimum over k is going to be at most as much as the minimum over c. So we can always say that phi sub k is less than or equal to phi sub c, is less than or equal to phi. And then the real problem here is to find some k that works nicely, that gives us a good approximation of the sparsest cut problem. And there are really two things that we want out of a good approximation to the sparsest cut problem. We want to find some k such that phi k is easy to compute, preferably polynomial time to compute. And we want to find some k such that phi k is close to phi, is as close as possible to phi. So it gives us the best possible approximation. Is this okay so far? Are there any questions so far? Okay. So what are some options? Well, what we generally find is that there's a tension between these two goals. In general, the k's which make this minimum easy to compute tend to be large. So for instance, if k was the entire set of n by n matrices, this would be easy to compute. This would be trivial to compute. But if we want phi k to be close to phi, we really want k to be small. So we need to find we need to find something in between, some set of matrices so that's easy to minimize over and yet small enough that it still gives us an answer that's pretty close to the original phi. So at one extreme, so a lot of the time, some of the best ways of doing this, some of the best relaxations come from looking at sets of matrices based on metric embeddings. So if f is a map from x to y, and x and y are metric spaces, I'm going to define d sub f to be the induced distance matrix. D sub f of ij is the distance between f of I and f of j. I'm sort of conflating distance functions on endpoint metric spaces and n by n matrices because they're really the same thing. So at one extreme, if I let my set of matrices be the set of metrics induced by maps into L1, then this turns out to be really close to the original sparsest cut problem. This turns out to be really close to the set of cut metrics. In fact, every element of K1, every L1 metric, every metric coming from a map to L1 is a linear combination of cut metrics. And so consequently, if we calculate the relaxation based on L1 metrics, we get the same as the original, same thing as the original sparsest cut problem. So this is a very good approximation. It's not even an approximation, it gives the exact answer. But because of that, it's difficult to compute. If calculating the minimum over cut metrics gives you the same answer as calculating the minimum over L1 metrics, then it's going to be equally difficult to calculate the minimum over cut metrics as it is to calculate the minimum over L1 metrics. So in order to get an approximation that's easier to compute, we need to take a larger set of n by n matrices. So one such set is if we take M to be the set of all n by n matrices. If we take M to be the set of all n by n distance matrices, then it turns out that the relaxation corresponding to M, phi sub M, is within a logarithmic factor of phi. This is a result of Linial, London, Rabinovich, and Oman and Rabbani. And it turns out that minimizing over the set of n by n distance matrices can be done reasonably quickly. In fact, there's a linear programming. In fact, being an n by n matrix, being an n by n distance matrix is a condition given by about n cubed inequalities, corresponding to symmetry, positivity, and the triangle inequality. And so you can find phi sub m using linear programming, and this is reasonably close to phi. And the way you prove that it's reasonably close to phi, the way you prove that it's logarithmically close to phi, is to use the following result: that every endpoint metric space embeds in L1 with log n distortion. So the way this works is that if you have a n by n distance matrix, then that corresponds to some endpoint metric space. That endpoint metric space embeds in L1 with the most logarithmic distortion. And so in particular, that n by n distance matrix is only about log n different from some L1 metric, from some element of K1. So every element of M is within a logarithmic factor of some element of K1. And so that means that the sparsity of any element of M is within a logarithmic factor of the sparsity of some element of K1. And so we have this logarithmic bound. Is this okay so far? Okay, so this is our first example of getting an approximation using metric embeddings. And we have this approximation phi m, which can be computed with linear programming, and where the accuracy comes from how well endpoint metric spaces embed in L1. The Goemans-Linial relaxation is another similar construction. So to construct the Goemans-Linial relaxation, we let n be the set of n by n distance matrices with negative type. And what negative type means is that an n by n distance matrix is negative type if it is negative definite apart from the all ones vector. It can't be completely negative definite because all its entries are non-negative. So we ask that it's negative definite on everything except the all ones vector, on the orthogonal complement of the all ones vector. And you can check, certainly, you can check that L1 has negative type. So in particular, all the L1 metrics are contained in N. Certainly, every n by n distance matrix with negative type is a n by n distance matrix. And so, well, since phi sub m, phi sub n, phi sub k1 are all minima over these different sets, we can see that phi is greater than or equal to phi sub n, is greater than or equal to phi sub m, and we saw before that phi sub m is within a logarithmic factor of phi. So phi sub n is at least within a logarithmic factor of phi. And furthermore, you can minimize over these distance matrices with negative type in polynomial time using something called semi-definite programming. It's a distance matrix is negative type, or a metric space is negative type if its distance matrix is negative definite on the orthogonal complement of the all ones vector. So in particular, here we're only going to be using two examples of negative type metric spaces. L1 is negative type, and the Heisenberg group turns out to be by Lipschitz equivalent to a metric with negative type. Okay? So is this okay so far? Okay, so this tells us that phi n, the Goemans-Linial relaxation, is at least as accurate as phi m, at least as accurate as the linear programming relaxation. The natural question is, well, how much better is it? And this has been open for a long time. So we can define the Goemans-Linial integrality gap. This measures the accuracy of the Goemans-Linial relaxation. It's the maximum of phi of c comma d divided by phi sub n of c comma d, where c and d are n by n matrices. So this tells us how the accuracy of the approximation decays as the number of as the size of the matrices involved increases. And it's known that the Goemans-Linial integrality gap, it's known that the Goemans-Linial relaxation is strictly better asymptotically than the linear programming relaxation by a theorem of Aurora, Lee, and Naor, who showed that this integrality gap is at most root log n times log n. Remember that the corresponding integrality gap for the linear programming relaxation, for the relaxation based on all metric spaces, was log n, and so we improve on that. So Aurora, Lee, and Naor improved on that by a root log n factor. And for a long time, it was conjectured, it was called the Goemans-Linial conjecture, that this relaxation, that this approximation is actually constant factor accurate, that in fact alpha of n is bounded, that in fact there's always a constant factor difference between phi and phi sub n. Equivalently, because of what we've been saying about negative type metric spaces and about embeddings, if this conjecture were true, it would be equivalent to say that it would be, if this conjecture were true, this conjecture is equivalent to saying that every finite negative type metric space embeds in L1 by a Lipschitz map. That the set of negative type metric spaces is within a constant factor away from the set of L1 metrics. But this conjecture turns out to be false. The first example was due to Cote and Vishnoi, who showed that in fact alpha of n grows at least as fast as a power of an iterated log. I think you can actually take the power to be 1 here. And their example was based on something called the unique games conjecture. And then Cheeger, Kleiner, and Naor came up with a more geometric example. They showed that alpha of n is in fact grows at least as quickly as log n to some power. But unfortunately, you can see that the power that they came up with is very small. It's on the order of 2 to the minus 60. And what their construction did was they showed that, well, like I said, the Heisenberg group is by Lipschitz equivalent to a negative type metric space. And so if you take a n-point subset of the Heisenberg group, that is a negative type metric space, and they showed that you can find an n-point subset of the Heisenberg group where the distortion of embedding that n-point subset in L1 is at least log n to some power. So, okay, so what Assaf and I have done, and what I want to talk about today, is we've made Cheeger, Kleiner, and Naor's example sharp. You can actually find an endpoint subspace of the Heisenberg group H5 such that any embedding of that endpoint subspace into L1 has distortion at least on the order of root log n. And so consequently, the Goemans-Linial integrality gap has to be at least on the order of root log n. And so this, and remember on the previous slide, we had an upper bound that it was at most root log n times log n. So this gives us the sharp exponent on the growth of the Goemans-Linial integrality gap. Okay? Any questions about anything so far? Okay, so this is about, this about covers the computer science background I wanted to, the computer science part of the talk. So if you came in late, or if you came in, or if I lost you during that first bit, this is the main thing we're interested in from the geometric point of view. We want to find some endpoint subspace of the Heisenberg group such that any embedding of that subspace into L1 has distortion at least root log n. And so from here on out, we're going to mostly we're mostly going to drop the computer science, and we're just going to look at embeddings. Is this okay so far? Okay. So what is the Heisenberg group? So the Heisenberg group is a nilpotent group, or it's actually a family of nilpotent groups, one in every odd dimension, of matrices of the following form. So we define H2k plus 1 to be a set of k plus 2 by k plus 2 matrices that are upper triangular with ones along the diagonal, with real numbers across the top row, real numbers across the rightmost column. And so you can check that we have 2k plus 1 dimensions, so thus h to the 2k plus 1. The Heisenberg group, this is the real Heisenberg group. There's also something called the integer Heisenberg group. If we require all of the coefficients to be integers, then we get a lattice in the real Heisenberg group. And that lattice has 2k plus 1 generators corresponding to, by abusive notation, I'm going to let the generator x sub 1 be the matrix where you have ones along the diagonal and zeros in every coefficient except for x1, and you let x1 equal to 1. And so you have 2k plus 1 generators corresponding to these 2k plus 1 coefficients, and you can check, just by doing some matrix multiplication, that these satisfy the following relations, that if you take the commutator of x sub I and y sub I, you get z. And if you take the commutator of any other two generators, you get 0. So this is a group. I want to talk about embeddings of this group, metric embeddings of this group. So I want to view this as a metric space. And so we can ask, what does this look like as a metric space? Well, we can understand the geometry of the Heisenberg group by looking at the Cayley graph of this lattice. So here is a picture of the Cayley graph of this lattice. So remember, the Cayley graph of a group is a graph where we have one vertex for every element of the group, and we connect two vertices by an edge if you can go from one element to the other by multiplying by a generator. And so here we have part of the Cayley graph of H3. Remember, H3 is a three-dimensional nilpotent Lie group, so we can identify it with R3, and we can identify the integer Heisenberg group with the integer points in R3. And you can check that if you multiply by x, then the x-coordinate increases by 1. If you multiply by y, you move along one of these blue wedges, then the y-coordinate increases by 1, and the z-coordinate increases or decreases according to the value of the x-coordinate. And if you multiply by z, then the z-coordinate increases by 1. And so you have a graph that looks like this. We have a bunch of vertical lines corresponding to z. We have a bunch of horizontal lines corresponding to x. And we have a bunch of lines that sort of tilt up and down depending on the x-coordinate corresponding to y. So what can we say about the geometry here? So for one thing, all of the relations that we saw on the previous slide, that the commutator of x and y is z, that the commutator of x and z and the commutator of y and z are 0, you can see those in this graph. So for instance, the fact that the commutator of x and z is 0 corresponds to the fact that if I start at any vertex and then I move in the x direction, z direction, back in the x direction, back in the z direction, I end up back where I started. The fact that the commutator of y and z is 0 corresponds to the fact that if I start at any vertex and I move in the y direction, z, y inverse, z inverse, I end up back where I started. And the fact that the commutator of x and y is z corresponds to the fact that there are a lot of spirals in this graph. That if I start at any point and then I move in the x, y, x inverse, y inverse, I end up 1 unit above where I started. And so, and it turns out that a lot of the geometry of the Heisenberg group is determined by these spirals. So here's one of these spirals. This corresponds to the fact that z is equal to xy, x inverse, y inverse. But there are actually a lot of these in this graph. So for instance, I can find a bigger spiral here. I can write z to the fourth as x squared times y squared times x to the minus 2 times y to the minus 2. I can find an even bigger one by zooming out like that. This corresponds to x to the fourth times y to the fourth times x to the minus fourth times z times y to the minus fourth is equal to z to the 16. And in general, I can do this for larger and larger spirals. I can write z to the n squared is equal to x to the n, y to the n, x to the minus n, y to the minus n, so I have spirals of arbitrarily large size here. So how do these affect the geometry? Well, these affect the geometry really in two ways. So one is that these spirals are all based on scalings. So this spiral here, this small spiral, scales up to this bigger spiral, and then we take this whole picture and we scale it up again to get this bigger spiral, and you can see that to go from here to here, what have we done? Well, we've doubled the x coordinates, we've stretched the x direction by a factor of 2, we've stretched the y direction by a factor of 2, and we've stretched the z direction by a factor of 4. And to go from here to here, we do the same thing. We take our picture, and you can actually see the original picture in this little corner here. In this corner here, you have a 2 by 2 by 4 block inside this bigger graph, which scales up to the entire graph. So for one thing, we have this scaling that we can replace x by x to the n, y by y to the n, z by z to the n squared. For another thing, these spirals get more and more efficient as they get bigger. So here you have a spiral path, this thick path of length 4 that moves up by distance 1. Here you have a thick path of length 8 that moves up by distance 4. So now the spiral is only half as efficient as the vertical line. Here you have a path of length 16 that moves up by 16 units. So now the spiral path is exactly as efficient as the vertical line. And in general, if I let n get larger and larger, I'm going to have paths of length 4n that move up n squared units. So as n gets larger and larger, these spirals get more and more efficient. And so what that means is that if I take 2 points in my graph that are very far apart, then the path between them, the shortest path between them, is mostly going to consist of red and blue edges. Because if it had a lot of black edges, if it had a lot of vertical edges, then you could replace all of them with one big spiral and save some length. So if we take a limit, if we continue taking this graph and scaling it smaller and smaller using this scaling, what we should get is some sort of structure where the shortest path between any 2 points basically travels along just the red and blue edges. And that structure is something called a sub-Riemannian metric. So a sub-Riemannian metric is like a Riemannian metric, except that a Riemannian metric defines lengths and defines distances. A Riemannian metric defines distances in terms of the lengths of curves, and it defines the lengths of curves in terms of the lengths of their tangent vectors. A sub-Riemannian metric does the same thing, except now in a sub-Riemannian metric, some of the tangent vectors have infinite length. So a sub-Riemannian metric is determined by a collection of subspaces, in this case these planes here, and you can see that these are the planes that are spanned by the red and blue edges. A sub-Riemannian metric is determined by a collection of planes that are called horizontal planes, and a norm on those planes as for a Riemannian metric. And then then instead of defining the length of all curves, we define the length just of horizontal curves. We define the length of curves that are always tangent to these planes. So in particular, you can see that all the red and blue edges that we saw on the previous slide, those are going to be horizontal curves. Those are going to be tangent to these planes, and so we can define distances using those lengths. But we also get more complicated curves. You can draw various spirals here that aren't limited just to moving in exactly the x direction or exactly the y direction. This metric is sort of the limit of the metrics on the Cayley graphs of the Heisenberg group. And what else can we say? We can say you can check that this metric supports the same scaling map that we saw for the Cayley graphs. In fact, what happens is that we have this collection of horizontal tangent planes that determines the metric. And then if we apply this scaling, you can calculate that it sends these horizontal planes to horizontal planes. And so it sends horizontal curves to horizontal curves. And so the distance between 2 points scales exactly by a factor of t. And so consequently, what can we conclude about what can we conclude about the geometry? One, we can show that the distance between 0, 0, 0 and x, y, z is approximately norm x plus norm y plus root norm z. And this basically this follows essentially from this scaling map. Because if I have a point like this, I can scale it down to get it in to put it into a small ball around the identity, connect it by a horizontal curve in that small ball, and then scale back up to get a geodesic from 0 to x, y, z. And also, because of this square root in the metric here, the z-axis turns out to be a lot bigger than the way we've drawn it here. It's actually relatively difficult to go from here to here, because to go from here to here by a horizontal curve, I basically have to take a spiral path that goes around like that. Because of that, distances between points that are vertically separated tend to be rather large, and you can show that the z-axis actually has Hausdorff dimension 2. So really, this picture of the Heisenberg group is not a very accurate picture geometrically, because we have all these sets that look one-dimensional, all these vertical lines that look one-dimensional, but are actually two-dimensional from the metric point of view. Is this okay so far? Okay. So what are we doing next? Okay. So what's the connection? So what's the connection between the Heisenberg group and the Goemans-Linial conjecture? Well, Lee and Naor proved that the sub-Riemannian metric on the Heisenberg group is actually bi-Lipschitz equivalent to a metric of negative type. Remember that the Goemans-Linial conjecture stated that every finite metric space of negative type embeds bi-Lipschitzly in L1. And it turns out that the Heisenberg group actually does not embed very well in a wide variety of spaces. In particular, Cheeger and Kleiner show that there's no bi-Lipschitz embedding from the unit ball in the Heisenberg group to L1. And so consequently, that means that finite subsets of the Heisenberg group are counterexamples to the Goemans-Linial conjecture. That is, they're finite negative type metric spaces that do not embed bi-Lipschitzly in L1. Why is this? Well, well, we can construct finite subsets of the unit ball that approximate the ball better and better. We can define x sub I to be a finite 1 over I dense set of points in the unit ball. And then we can let I go to infinity. If the Goemans-Linial conjecture holds, then there's going to be a sequence of bi-Lipschitz embeddings of x sub I into L1 that all have uniform constants. And so consequently, there's going to be some limit of these bi-Lipschitz embeddings consequently, these bi-Lipschitz embeddings are going to converge to some limit f from the unit ball into L1. But by Cheeger and Kleiner's theorem, this does not exist, and so there's a contradiction, and so we can't have a sequence of bi-Lipschitz embeddings with uniform constants from these x sub I to L1. So that's the Heisenberg group, and that's that's how we want to connect it to the Goemans-Linial conjecture. Are there any questions so far? Okay. So now let's try to prove this. Now let's try to prove that the Heisenberg group does not embed bi-Lipschitzly in L1. In general, like I said, the Heisenberg group turns out to be difficult to embed in a wide variety of spaces. So the first non-embeddability result for the Heisenberg group is a result of Ponceau and Sems, who proved that there's no bi-Lipschitz embedding from H2k plus 1 to Rn. And this result is based on differentiability. The way they prove this is to show, Ponceau showed that every Lipschitz map from the Heisenberg group to Rn is what's called Ponceau differentiable almost everywhere. What it means to be Ponceau differentiable is that that near almost every point in the Heisenberg group, the map approaches a particular structure. If you take smaller and smaller balls around almost any point in the Heisenberg group, then the map is going to converge to a particular structure on those smaller and smaller balls. In particular, Ponceau differentiability means that on sufficiently small scales, this map F is close to a homomorphism. The problem you run into is that there aren't very many homomorphisms from the Heisenberg group to Rn. In fact, any homomorphism from the Heisenberg group to Rn sends the center to 0, and so that means that any Lipschitz map to Rn collapses the z direction, and that means there can't be any bi-Lipschitz map from the Heisenberg group to Rn. And so this is a theorem that works in Rn. You can actually generalize. It works in any Banach space with the Radon-Nikodym property. So that includes LP for p greater than 1, less than infinity. But what we really want is we want non-embeddability results into L1, and non-embeddability results into L1 turn out to be somewhat harder. So like I said, Cheeger and Kleiner showed that there's no bi-Lipschitz embedding from the Heisenberg group to L1. And the reason that L1 is more difficult than Rn is because a lot of differentiability results really don't work in L1. Remember, Ponceau's theorem said that any Lipschitz map from the Heisenberg group to Rn had to be differentiable, had to be locally like a homomorphism almost everywhere. This does not hold for Lipschitz maps to L1. The standard example of this is the following map, which embeds an interval into L1 isometrically. We define a map F from 0, 1 to L1, where we send f of t to the characteristic function of the interval from 0 to t. And you can check that this is an isometry. This is an isometric embedding of the interval into L1, but it's not linear anywhere. If we zoom in, or if we look at this on any small neighborhood in the unit interval, it's never going to get closer and closer to a linear function. This map can never be approximated by a linear map, and so we don't have the usual notion of differentiability. So in order to prove that the Heisenberg group does not embed into L1, Cheeger and Kleiner had to define a different notion of differentiability, and it's a notion of differentiability based on cut metrics. So is this okay so far? Is this example clear? Okay, so Cheeger and Kleiner defined a notion of differentiability based on cut metrics. Remember a cut metric was a metric that was either 0 and 1. You have some cut of your set X into S and S complement, and you say that the distance between any 2 points in S is 0, and the distance between 1 point in S and 1 point in the complement of S is 1. And we said before that every L1 metric can be written as a linear combination of cut metrics. So here's a formal statement of this, that if F is a function from the ball to L1, from the unit ball to L1, then there's a measure mu called the cut measure on the set of subsets of B, such that the distance between f of x and f of y is the integral of cut metrics with respect to this cut measure. This is called the cut cone decomposition of a metric, because we write the induced metric in terms of some linear combination of cut metrics. And so what this means is that instead of studying embeddings into L1, we can study subsets of the Heisenberg group. We can study subsets of the ball. In fact, we can do a little bit better. So we can study F by studying cuts in H2k plus 1. In fact, we can do a little bit better. Let me introduce a little bit of notation. An open set in H2k plus 1 has Hausdorff dimension 2k plus 2, because remember the vertical line has Hausdorff dimension 2. And any subsurface that separates two open sets has to have Hausdorff dimension at least 2k plus 1. So I'm going to call the area of a set its 2k plus 1 dimensional Hausdorff measure. I'm going to call the volume its 2k plus 2 dimensional Hausdorff measure. And then you can show that if we take the cut cone decomposition of a Lipschitz map, if F is Lipschitz, then its cut measure is supported on sets where the boundary has finite area, and furthermore, we can bound the total area of that boundary. The integral of the area over, with respect to the cut measure, is at most the volume of the ball times the Lipschitz constant of F. So in particular, we don't have to consider arbitrary subsets of the Heisenberg group. We can consider sets in the Heisenberg group whose boundary has finite area. And these, it turns out there's a fair bit of analysis done on sets like this. So for instance, Franchi, Serapioni, and Seracasano proved a rectifiability condition. They show that if S is a set whose boundary has finite area, then the boundary of S is what's called rectifiable. That near almost every point in the boundary is close to a plane containing the z-axis. That is to say, if I take a point on the boundary and I take a sufficiently small ball around that point, and then I scale that ball up to the unit ball, I'm going to get something that gets closer and closer to a vertical plane. This may be a little. This may seem a little bit surprising because, well, okay. So you can imagine sets of finite area in the Heisenberg group. You can imagine, say, some subset of H3. Here's H3. I consider some nice round sphere. Certainly, this looks like it has tangent planes, but it's not really clear why these tangent planes should be vertical, why they should contain the z-axis. But the reason that this happens is because of the scaling we have in the Heisenberg group. Even if we have some nice, smooth, round sphere in the Heisenberg group with nice Euclidean tangent planes that are sort of slanted like this, when we zoom in using the Heisenberg scaling, when we stretch x by n, y by n, z by n squared, that slanted tangent plane is going to tilt more and more until it becomes closer and closer to vertical. So every reasonably nice surface in the Heisenberg group has vertical tangent planes almost everywhere. Even if from the Euclidean perspective the tangent planes aren't vertical, when we apply the Heisenberg scaling, they get they become vertical. Is this okay so far? So how does this affect? So how does this help us prove that the Heisenberg group does not embed in L1? Well, for almost every point in the unit ball, so what Cheeger and Kleiner do is they show that for almost every point in the unit ball, so this tells us that all of our cuts are rectifiable, all of our cuts have vertical tangent planes. Cheeger and Kleiner do some analysis, and they show that in fact for almost every point in the ball, you can find some small neighborhood of that point, so that most of the cuts are close to vertical on that smaller ball. If the cuts were exactly vertical, then then our embedding would have to send 2 points that are separated by a vertical line to the same point. Because if the cuts are exactly vertical and you have 2 points that are separate that lie on the same vertical line, then they lie on the same side of every cut. If all the cuts are exactly vertical, then all the vertical lines get collapsed completely. So if all the cuts on B prime are close to vertical, then that means that the restriction of F to B prime is close to a map that's constant on vertical lines. And so in particular, that means that F has to nearly collapse these vertical lines, and that means that F can't be a bi-Lipschitz map. So we can take a embedding, we can represent it in terms of a sum of cuts, we can do some analysis on the boundary of those cuts, and we can use that to show that the Lipschitz maps from the ball to the Heisenberg group have to collapse vertical lines at least to some degree. This is not quantitative because this rectifiability result is not quantitative. We have no information on how small a ball we have to take before we get closer and closer to a vertical tangent plane. But Cheeger and Kleiner and Naor made this result quantitative. They showed that if you have a ball, if you start with a ball of radius 1, then you can find then for any delta, then there is a delta greater than 0, such that for any epsilon and any one Lipschitz map F from the ball to L1, there's some smaller ball of radius epsilon, such that the restriction to that smaller ball is about log epsilon to the minus delta close to a map that's constant on vertical lines. And so this gives a quantitative version of the previous result. This implies that the Goemans-Linial integrality gap is at least log n to some power. Unfortunately, the problem is that this power ends up being very small. The delta ends up being around on the order of 2 to the minus 60. So So now I guess we get back around to where we started. What I and Assaf have done is we've proved the sharp exponent. We've shown that we can actually take this exponent to be 1/2 here. And the way that this works, the main difference between what Cheeger and Kleiner and Naor did and what I and Assaf did is that this result really depends on sufficiently small balls. This result uses rectifiability, uses the fact that that a finite perimeter set is close to a vertical tangent plane on sufficiently small balls to get a bound on what happens to the map on sufficiently small balls. What Assaf and I have done is we've proved an inequality that works that doesn't necessarily say that arbitrarily small balls get collapsed, but what it shows is that on average, every ball gets collapsed. So we prove the following inequality, that if k is greater than or equal to 2, b is the unit vol in h2k plus 1, and if z is the generator of the z-axis, then for any Lipschitz map from the Heisenberg group to L1, this inequality is satisfied. So let's unpack this inequality. So this inequality, we're looking at this ratio here between the distance in L1 between f of x and f of x z to the t, divided by the distance between x and x z to the t. So if the map were bi-Lipschitz, then this ratio would be bounded below. So if the map were bi-Lipschitz, this ratio would be bounded below by a constant. If the map were bi-Lipschitz, then this integral would be, I guess it would be the volume of the ball times that constant squared, so it would be some other constant. And then we would be integrating that constant from 0 to 1 with respect to dt over t, and you can check that that integral is infinity. So this, in particular, this excludes the possibility of a bi-Lipschitz map, but also it also gives us very strong bounds, very sharp bounds on the scale of on how much distortion there has to be. You can check that if instead of requiring this to be a constant, if I say okay, there has to be some distortion, but I want as little distortion as possible, well, you can check that if this is bounded below by c, on all balls of radius epsilon, if you have a bound on the distortion above scale epsilon, then you can work out this inequality and you can show that there's a relationship between the scale at which your map is undistorted and the amount of distortion you have, and that relationship gives you this bound that alpha of n is at least on the order of root log n on the integrality gap. Is this okay so far? Okay, I guess I have to go very quickly to give a very brief sketch of how this works. The basic idea, okay, so the basic idea of the proof of this is that we're going to work in a very similar fashion to what Cheeger and Kleiner did. We're going to use the same cut cone decomposition of the induced metric. And so that instead of studying maps, we can study subsets of the Heisenberg group. If we reduce to subsets of the Heisenberg group, this is the inequality that we want to prove for subsets of the Heisenberg group. One way to interpret this is that this quantity here measures how far this set S is from being vertical. If S is a union of vertical lines, then this symmetric difference is always 0, and so this quantity would be 0. And if S is not vertical, if we start adding bumps to the boundary of S, if we start perturbing the boundary of S, then this ratio is going to increase, so this integral is going to increase, but also what this theorem says is that if we start adding irregularity to the boundary of S, it's also going to increase the boundary of S. And one way of thinking about one way of thinking about what we did is like I said, we're following a similar outline to what Cheeger, Kleiner, and Naor did. They showed that surfaces in the Heisenberg group are rectifiable, which is to say they have vertical tangent planes almost everywhere, and then they use that to prove a sort of differentiability result for maps to L1, that at sufficiently small scales, a map to L1 is going to be close to a map that's constant on vertical lines. What we do is we replace rectifiability here with a notion called uniform rectifiability. So rectifiability is really a notion about what happens on sufficiently small scales. So there are very complicated sets. There are very complicated sets that are rectifiable. For instance, say, if I take the Koch snowflake, the curve that you get by starting with a triangle and adding smaller triangles on the sides like this. The Koch snowflake, if I repeat this process infinitely many times, the Koch snowflake is not rectifiable. It never has tangent planes. No matter how close you zoom in, you still have a bunch of roughness. But if I don't repeat this infinitely many times, if I only repeat this, say, 100 times, then the result is a rectifiable curve. It's not a very nice rectifiable curve because you have to zoom in to a scale of 2 to the minus 100 in order to see that it's actually made up of line segments, but it is a rectifiable curve. It is not, however, uniformly rectifiable, or it's not uniformly rectifiable with any reasonable constants. So I don't want to get into the definition of uniform rectifiability, but one definition of uniform rectifiability is that a set is uniformly rectifiable if, for all but a few balls, the intersection of a ball with the set is close to the graph of a Lipschitz function with small Lipschitz constant. That is something that's true for something like, say, the square. If I take a random ball on the boundary of a square, it probably doesn't see one of the corners, and so if I take a random ball in the square, as long as it avoids the corner, the square is going to be close to a Lipschitz graph on that ball. But in the Koch snowflake, if I take a random ball, there are so many corners that I'm very likely to see a corner. And so uniform rectifiability is a way of telling curves that are nearly fractal, like this Koch snowflake, apart from curves that aren't, like this square. So what Assaf and I showed was that surfaces in the Heisenberg group are made of uniformly rectifiable pieces in a Heisenberg sense. And by that, I mean that surfaces in the Heisenberg group can be decomposed into sets so that each of the pieces in the decomposition can be approximated by intrinsic Lipschitz graphs on most balls. An intrinsic Lipschitz graph is a Heisenberg generalization of the notion of a Lipschitz graph. It looks like this. And you'll notice that this has a lot of nice properties. This is topologically very nice. It's homeomorphic to a plane. It has Hausdorff dimension 3. The only really bad thing about it is that it's very spiky. It can be much more pointy. It can have many more spikes than a graph in Rn because of this Hausdorff condition, this Hausdorff dimension of the vertical lines. Because the vertical lines are all two-dimensional, that means that there's a lot more room to have spikes, a lot more room to have complications along those vertical lines. But it's still a fairly reasonable surface. It can be defined in terms of some function on a plane, and we can do analysis on this surface using in terms of a function on the plane. And so that's what we do. We use the theorem of Austin, Naor, and Tessera to show that on an intrinsic Lipschitz graph, the inequality that we want is satisfied, and then we show that if you have a graph that's approximated by, if you have a surface that's approximated by Lipschitz graphs on most balls, if you have a surface that's uniformly rectifiable in this Heisenberg sense, then it also satisfies our inequality. So that's the very brief sketch of the proof. Let me just mention a couple of open questions here. One, you may have noticed that that in all the theorems I required k greater than or equal to 2, which means that I'm looking in H5 rather than H3. And it seems like this is important. It seems very possible that this inequality does not hold for H3, that somehow H3 embeds in L1 much more nicely than H5. And very roughly, the reason why this happens is that if we take these graphs like this, what we really do is we slice this into pieces to get a graph over some smaller Heisenberg group, and then we do analysis on that smaller Heisenberg group. That's going to be impossible in H3, because if I slice this into pieces, these are going to be graphs over some one-dimensional Heisenberg group, and there is no one-dimensional Heisenberg group. So in H3, you need a different inequality than this one here. And we don't have that inequality, so it's very possible that the inequality does not actually hold in H3. And then a second open question. I've been calling this property of being approximable nicely by intrinsic Lipschitz graphs. I've been calling it uniform rectifiability, but that's cheating a little bit, because uniform rectifiability in Rn is an important property that has definitions, that has many different definitions. You can define it in terms of singular integrals, beta coefficients, Corona decompositions, something called the big pieces of Lipschitz graphs property. There are about a dozen or more than a dozen definitions of uniform rectifiability. What we have is one particular notion. We've used Corona decompositions to study one class of surfaces in the Heisenberg group, and it's very natural to ask, do any of the other definitions, singular integrals, beta coefficients, and so on, do any of these also generalize to the Heisenberg group, and other interesting things we can prove using them? Okay, thank you.